Good morning, good evening, or even good night to whoever that's watching this video. My name is Adrian, and I'm from Xiamen University, Malaysia. And the purpose of this video is a presentation given by me talking about the connected space in topological sense to R. So first off, we're going to start from topological space, and we're going to talk about what is a connected space in topological space. So the first definition is, of course, the separation. So let X to be a topological space. A separation is defined to be a pair of disjoint, non-empty, open subsets of X. So if you call these two, if this pair U and V, then the U and V has to satisfy such condition also. This condition is that U union V must be equal to X. So if we say that a space X is connected, if you cannot find such separation. If you can find such separation, then it is disconnected. So naturally, in the space X, you want to talk about connected subspace also. So a connected subspace is with the same definition as the above, but we talk about it in a subspace topology. So here is a nice property of how a connected subspace in a disconnected space uh, looks like. Okay, so this is how it looks like actually. So before I talk about proof, so intuitively you can see that the subspace Y cannot be the connected subspace Y cannot lies in between separation U and V, meaning that Y cannot exist in U and Y cannot exist in V at the same time, or not, Y will be disconnected. So this will contradict to our assumption. So the proof is as what I've said just now. So you take the intersection of them, and then this shows that is one of the intersection must be empty, else it will be a contradiction. So Y has to be in U entirely or V entirely. So next, this is another very nice properties, which is that an arbitrary union of connected subspaces of X that has a point in common. So each of the connected subspaces must have a point in common. So the arbitrary union of them must be connected too. So the proof of this, the proof idea of this is very easy. You prove by contradiction, and then you say that, oh, there's a separation, and then by the previous lemma, the the common point, let's say A must exist in U or V since U and V is disjoint, and then the previous lemma tells us that if it's in U, then it must lies entirely in U. If it's in V, then it must lies entirely in V. And then this will contradict the non-emptiness of U and V. So next, which is another nice properties of a connected space, and or you can say there is a continuous. So this theorem tells us that the continuous image of a connected space is quantum. Okay, this is very easy to prove bisexually. Okay, and then another nice property is that a finite Cartesian product of connected spaces is connected. But we will not prove this because this proof is a little bit long. So you can look at the reference that I put there for you guys. So next is that. So before we talk about Rn space, we want to talk about R, and then actually for all the properties that we have presented before, we have established before, it all of them is also true for R and Rn, because R and Rn is also one of the topological space. Okay, and in this section, we found out that intermediate the one of the nice big theorem in calculus is that the intermediate value theorem. So intermediate value theorem does not really rely on the algebraic properties of R. Instead, it relies on the order properties of R. So first, we're going to talk about it. So we're going to talk about all this, and then we'll prove the more general setting intermediate value theorem, and then we'll move on to the Rn case. So now we want to define what is a linear continuum. A linear continuum is a simply ordered set that satisfies these two conditions. Okay. very easy. And we define what is the intervals. Or if anyone doesn't know what is it, you can stop and look at it. So these are some figures. And yes, of course, if you want to talk about a set, ordered set, simply ordered set, then if you want to make it a topological space, we need to tell you what is the basis. We need to tell you what is open inside of it. What can generate all these different sets. So all these sets are the following. So if it has no smallest and largest element, then it will just be open interval. If it has the smallest, then it will be this half closed interval. So the third one as follows. So again, we talk about what is the definition of rays. It's just intervals with extension to infinity. And this one of the nice theorem. The proof is also a little bit long, so we will not present it here. So it tells us that if L is a linear continuum, okay, equipped with the order topology, then L must be connected, and so are all the intervals and rays in L. Okay, so again, if anyone is interested in the proof, you can look at this book. Okay, and from this theorem, the consequence of this theorem is very straightforward. One of them is R is connected because R is a linear continuum. So does intervals and rays in R. And now finally we can talk about the general setting, the more general setting of an intermediate value theorem in topological space. So same thing, we let F to be a continuous map from X to Y, but what's different here is that we only want X to be a connected space, but Y, but the space Y we does not want it to be R anymore. So we can make Y more general. So if Y is just an ordered set in a order topology, then the intermediate value theorem still works. Okay, so the proof are also easy. I'll not talk about it. So what is connected subspaces in real R, real line R? So yeah, so this is also a very nice properties of subspaces in R lah. So if it's in an interval, then it must be path connected, it must be connected, and if it's connected, it must be path connected, it must be an interval. All of these are equivalent. So we will not prove this also because it's a very long statement, a bit tedious proof. So you can refer to this book. And then finally, the intermediate value theorem for connected set in Rn. So we see that this is a special case of what we have proven just now. So this special case is that we let X to be a but D now is a connected subset of Rn. Okay? And we let Y to be R. So Y is a linear continuum, so it's okay. So we can pick R. And by our previous this theorem, we know that the image must be integral since it is connected. Okay, and now we'll go a little bit off topic for the sake of my example. So we talk about a little bit about a path connected. So what is a path? A path is a continuous function that maps from a closed and bounded subset of R to our space X. So we say that there is a path in between X and Y. You can only if this sort of function exists with the condition f equals to x, f equals to y. So straightforward, if a topological space is a path pointer, then every pair of points in X must have a point in between, have a path between them. So there's another nice theorem is that if X is path pointer, then it must be connected. Okay. So now we move on to our example. The first example is I'm going to show that x equals to R2 set minus Q2 is actually connected. So what's the idea of this? So let's think about it. So we cannot have two tuple of rational points in here, but we can have one irrational, one rational. Then if we move along the irrationals straight, either horizontally or vertically, then we can move up and down. So move up and down. So we are in a 2D plane. So you can if you want to go from here to here, then all you need to do is move horizontally and move vertically. Then you get to the point. Then this will create a path for you. But we need to talk about all cases that can happen, right? So these are all the 9 cases that can happen. And interestingly, you can actually define a path. So for case one, case two, case three, case four, six, seven, eight, the path can be goes like this, like a box. So it's either x is irrational first or y is irrational first. Okay. If y is irrational first, they will follow the red path. If x is irrational first, you will follow the blue path. And this is a special case, case five. So this is a case where you want to go from AB to CD, but this one D is not irrational, so you need to stop halfway. It is irrational. You stop at an irrational y equals to irrational points, and then you move horizontally and you go up again. So key sign is the same thing, but it's a mirror. And yes, we're going to talk about the topology sine curve, which is um which is interesting. So we're not going to talk about why the closure is this. It is very obvious if you look at the curve. So the red line is the limit point. And we want to show that the S bar is actually not path connected. So we prove by contradiction. So we first assume that it is path connected, then you have this function f, and then we want to create a sequence of Tn such that Yt does not converge. So this will contradict the continuity of f. Okay, so we want to find such xtn. So u1 under un gives you. So x now is a function. So we will uses the intermediate value theorem on the function xt to find such tn that gives you un, that gives you yt equals to -1, and that does not converge. And that's all from my presentation. Hope you enjoy it. And these are my references. So if anyone is interested, you can go and look at it. Thank you very much, and have a good day.